All right. Well, guess who finally remembered their YouTube password? Hey guys, it's me, ActiveXSploit, back again with a new video, crawling out of the shadows of the internet like a stealthy payload after almost 2 whole years, I guess. I know what you guys are thinking. Did the hacker finally get hacked? Nope, I was just stuck in an infinite loop of procrastination. Nah, I'm just kidding. Actually, I had to take a long break due to other important things in my life. However, I'm finally back and I'll be regularly uploading videos on the channel now. So, let's reboot this InfoSec journey together, shall we? So make sure to leave a like on this video, subscribe if you haven't already, and let's exploit some epic content. By looking at the thumbnail of the video, you might have already guessed what we are going to talk about. Today, we're going to be diving into a topic that is critical for any red teamer or an ethical hacker, that is bypassing EDR API hooks using direct system calls. We'll break down how EDRs hook into API calls, why direct syscalls can bypass those hooks, and walk through a clear step-by-step approach to implementing this method. This video is all about understanding the fundamentals and applying them effectively, so stick around, there's a lot to unpack, and let's jump right in. So, first of all, let us talk about what is a syscall or what is a system call. In the old days, computers weren't really that advanced as they are right now, and consider that you are running an application on that computer, and if the application crashes due to some reason, that application crash would actually cause the whole operating system to crash, which is very fatal, isn't it? This was because older processors actually didn't have any sorts of memory isolation or protective mechanisms in order to prevent the normal applications from accessing critical components of the kernel. However, everything changed in the newer modern generation processors where memory isolation and protective mechanisms were introduced, which was in order to prevent normal user applications from accessing the critical components of the memory directly or the kernel directly. This mode is known as the protected mode, where the protected mode introduced many safeguards and prevented the operating system from crashes by isolating the running user applications from each other, which was basically done via virtual memory and privilege levels or rings. Now, on Windows, there's two types of modes, the user mode and the kernel mode. The user mode is where all normal user applications run, and the kernel mode is where all the critical kernel and device-based drivers are located at. The user mode is referred to as ring 3, whereas the kernel mode is referred to as ring 0. So, as you can see in this image, ring 3 is the user mode, which is the least privileged, and ring 0 is the kernel mode, which is the most privileged. Now, whenever an application needs to execute or perform a privileged system operation, the processor will have to switch to ring 0, which is the kernel mode, and hand the control flow or the execution flow to the kernel mode. And once the execution of the privileged operation is completed, the control flow or the execution flow is once again returned back to the user mode. And this is exactly where the role of a syscall comes into play. A syscall is a CPU instruction that is used to perform a transition from user mode to the kernel mode by the application whenever they need to execute or perform a privileged system operation. On 64-based CPU, if you want to perform a syscall, the instruction used is going to be syscall itself. And on x86-based CPU, which is the 32-bit architecture, if we want to perform a syscall, the instruction which we use is int2eh. Alright, so next we have the practical usage of a syscall. Now, this is an image from x64dbg, which shows disassembled version of the NT-read virtual memory native API call. And now, this is the part where I want you guys to pay good attention at, because this is definitely going to be used later on. So over here in this image, as you can see that we have multiple assembly instructions, right? And so there's like a bunch of assembly instructions in here, and these group of assembly instructions are what we refer to as a syscall stub. And this is a syscall stub for the NT-read virtual memory API call, okay? And there are multiple syscall stubs of different native API functions in the ntdll.dll file. And what exactly do I mean by this? Well, there's going to be a separate syscall stub just like this for NT-open process, and then there's going to be a separate syscall stub for another API call such as ntallocate virtual memory. So there's going to be like, multiple syscall stubs for each native API function in the ntdll file. Uh, Next, at first, the NTRead virtual memory function from the ntdll.dll is responsible for preparing the necessary arguments on the stack for the system call. And just after that, we have a move instruction, which is used to move the SSN number to the EX register, where the SSN number here is 3F. Now, what exactly is an SSN number? So, an SSN number, or SSN, stands for system service number, and the system service number is used to identify a specific system call or service provided by the Windows kernel. Okay. However, there's actually a small problem in here. The SSN changes between different Windows OS versions, and in some cases, it also changes between different build versions of the same Windows operating system. Okay. And finally, after that, we have the syscall instruction, which is used to switch into the kernel mode. So that's a nice and a short intro on what exactly a syscall is and why do we even need it. If you want to study about it in depth, you can always hit Google up and ask for more information. And even in the description box below, I'll put some links to some great resources out there which do a fantastic job at explaining syscalls and direct system calls in a very clear manner, so that you can easily refer to it. Now, moving on. Next, we have an image showing an example of hooked API call by an EDR, and in this case, the security solution used is Bitdefender. If you look closely at this disassembly of the hooked API call, it is completely different than the unhooked one as shown previously in this image. Okay. Now, here, the first instruction itself is a jump instruction to a different memory region, which is pretty weird, right? So where exactly is our execution flow jumping to? Well, it jumps to a region of the protective DLL owned by the EDR, which is injected in our application's memory space by the EDR itself. And its function is to determine whether if the API call being executed is performing anything malicious or not. If the EDR detects any sorts of malicious activity, it is going to immediately block further execution of code, whereas if nothing malicious is detected, it allows the program to continue its normal execution, which is followed by a syscall instruction here, as you can see. And in this image, as you can see, Bitdefender actually injects its hooking DLL into the memory space of a normal application and hooks specific API calls which can be used for malicious purposes, such as NT-open process or NT-allocate virtual memory or NT-create threadx and so on. So what can be the solution to this problem? How can we execute our shellcode in memory, or how can we inject our DLL into a remote process without getting detected by the EDR? Well, there's multiple methods out there which we can use in order to bypass the API hooking utilized by the EDR, and one of them is direct system calls. So imagine it like this. What if we define our own assembly procedure that consists of a custom syscall stub which performs a syscall for us instead of going to the ntdll file which is hooked, and also define our own native API function prototype in our code and use them instead of using the hooked functions in the ntdll file. This will bypass the EDR as we are not touching the hooked functions at all, and hence this, ladies and gentlemen, is what we call as direct system calls, where we define our own syscall stub and directly invoke the kernel through the system call mechanism, which bypasses the user mode API layer completely. Okay, so direct system calls refer to the process of bypassing the standard Windows API and invoking kernel level system services directly via the syscall interface without relying on the implementation in ntdll.dll or any other user mode library. This technique involves the usage of system service numbers and issuing the appropriate syscall instruction to transition from the user mode to the kernel mode. So, will this bypass all the EDRs in 2024 or 2025? Actually, no, it won't, because a major limitation of this technique is that it is very noisy. And by noisy, I mean that EDRs can easily pick up or easily detect if a syscall instruction is executed outside of the ntdll's memory space. However, this technique still manages to bypass some AVs or EDR solutions out there, but it won't really get past through the extremely good ones such as CrowdStrike or Sentinel-1. So that's all for the theory portion. Now, I do understand that majority of you guys will find it difficult to understand so much information, that too which is completely theoretical, but don't worry, it is going to make a lot more sense in the practical portion. So with that being said, let's dive deep into the practical portion. Okay, so let's dive into the practical portion, shall we? So the practical part of implementing direct syscalls is going to be divided into three portions or three stages. The first stage is going to be all about setting up our development environment, where we have to make some changes to our setup in order to make our code compile. The next stage is about defining our own syscall stub and the function prototype, in which we'll generate the function prototype using syswhispers1 and manually define our assembly procedure for performing a direct syscall. And after that, the final stage is where we'll be coding our remote process injector, okay, where we'll inject shellcode into a remote process using the 4 standard native API calls, which are NT-open process, NT-allocate virtual memory, NT-write virtual memory, and NT-create threadx. So, firstly, for the development environment, I have Visual Studio 2022 on my system along with Visual Studio build tools already installed. So make sure that you also have the same setup like mine. And as far as the test VM is concerned, I have a Windows 10 virtual machine running on VMware over here, and I also have a Kali Linux 2024.2 running on VMware. Okay, so first of all, we'll go back to our Visual Studio 2022, and now I want you guys to create a console application project in C++ like this. Okay, you can just go up over here and search for console app. As you can see, we have the console application in C++. So we'll just click on this, next, and we'll just assign it a project name. We can just say direct syscall, okay, like this. We click on create. And there we go. I have the window open for me. So it should look something like this for you once you have successfully created a new C++ console application project. So after this, what I want to do is I'm going to go to this project over here. Okay, this is the project name, and I'm going to click over here, the right click. I'll go to build dependencies, build customizations, and make sure that you check the MASM over here. Okay, so you just have to check it like this, and then finally click on OK. All right. After this, I want you guys to go to the source files and right click on source files and then click on add, then go to the new item. And now I want you guys to add a file with .asm extension, and this is where we'll be defining our own custom syscall stubs. Okay. Also, please make sure that this assembly file, okay, this asm file has a different name than the source file over here. Okay, the source file is directsyscall.cpp, because if the names of both the files become same, then your code won't compile and it's just going to give you errors. Okay, so we'll just say syscall.asm, and there we go. Now, the next thing which I want you guys to do is right click on the syscall.asm, then click on properties. And after this, make sure that the item type is set to Microsoft macro assembler for you. By default, it should be set to does not participate in build. But if it's like this, I want you guys to change this to Microsoft macro assembler and then click on apply. And finally on OK. After this, I want you guys to go to the header files and right click on this header file, then go to add and click on new item. And over here, we'll just say syscalls.h, or let it be syscall.h. Okay, it can be anything which you want. Now, this header file is going to contain our function prototype for the native API calls which we're going to use in order to perform shellcode injection, right? So after this, finally, we need to enable static linking. So in order to enable static linking of the binary, of the compiled binary, okay, we just go to direct syscall. We'll right click over here, properties, and then I want you guys to go to C++ and code generation. And over here, I want you guys to select the runtime library and change this to multi-threaded, which is /empty. Finally, click on apply and OK. Okay, so that's it. We're finally done with the first stage of implementing direct syscalls. We have configured our development environment so that it compiles our code correctly. Moving on, next we have the stage 2, which is setting up our function prototype and custom syscall stubs. So for this, I want you guys to clone this GitHub repository of syswhispers on your Kali Linux machine or your Windows machine. Okay, that can be your choice. Now, syswhispers is a tool that can automatically generate the function prototype, uh, which is a header file that consists of the function definitions of the native APIs which we wish to use. And it also generates the custom syscall stubs for the functions we need. Now, if you know a thing or two about syswhispers 1, then you might also know that syswhispers 2 also exists. And it is far better as compared to syswhispers 1 because syswhispers 1 is like completely static. Okay, syswhispers 2 can actually generate a syscall stub which can dynamically resolve these SSNs for us. Okay, these native API function SSNs. Okay, whereas syswhispers 1 is completely static and it relies on the exact operating system version of the target to generate those SSNs. So in a real world engagement, you should probably go with syswhispers 2 because it doesn't rely on the exact operating system version of the target for generating these SSNs. Instead, it does it dynamically. And that is because in a real world scenario, we won't always have the information on exact operating system version of the target. And for the sake of this video, we're going to utilize syswhispers 1 instead of syswhispers 2 because we're going to stick to the absolute basics, right? So that you guys get a clear understanding of how this works. If you wish to use syswhispers 2, that's completely fine, and the procedure is literally almost similar. You only have to include an extra file in your project in case you're, utilizing syswhispers 2 for this method. Okay. Also, even if syswhispers 1 can generate the syscall stuff for us, we won't be utilizing it, and we'll only utilize the function prototype generated by it. Okay, and that is because we want to manually define our own syscall stub instead of going with the tool's syscall stub. Okay, and the reason behind that is I want to show you guys how exactly this works, right? So moving off to our Kali VM, once you clone the syswhispers repository, first of all, we'll have to install the required dependencies by the tool using the pip command. So if I just run ls-la, as you can see, I have requirements.txt. So I'll just say pip3 install-r requirements.txt and press enter. And as you can see, it says requirement already satisfied. That's because I had already installed them earlier. And once you're done with installing the required dependencies, now we're going to finally run the syswhispers tool. That's going to be via this command, python3/syswhispers.py-f -open process, allocate virtual memory, write virtual memory, create thread x, and then we specify the operating system version which we are targeting, which is Windows 10 in this case, and then we specify the output with the -o flag. So over here in this command, we specify the native API functions which we want to use in our function prototype using the -f argument, and we finally specify the operating system version, which is Windows 10 in our case, using the -v argument, and we use the -o argument for storing the output. Okay, so we're just going to store it to, let's say, syscalls 1. And there we go. As you can see, we have two files written to the disk, which is syscalls1.asm, where this is the custom syscall stub, and the other one is the syscalls1.h, which is the function prototype. Okay, it's the header file which we were talking about earlier on. Now I want you guys to copy the contents of the syscalls_1.h file, .h header file, into our syscalls.h file over here. Okay, so I'll just go back to my Kali VM and I'll quickly cat this out. And I'll copy everything from here. Copy. I'll go to my Visual Studio and I'll just paste the contents of the syscall_1 header file into our own header file. Okay. So that's it. We've defined our function prototype successfully. After this, one more thing that's left is writing our own syscall stubs. Before we actually write our own syscall stub, first thing which we want to do is let's gather the SSNs of these 4 native API functions, which is open process, create thread x, allocate virtual memory, and write virtual memory. Okay, so what we want to do is we want to gather the SSNs of these 4 native API functions, which will be used in our syscall stubs later on. Okay, so how do we exactly gather these SSNs? I'm going to show you guys 2 ways in order to do so. So first of all, I want you guys to go to your Windows system and then open up a command prompt. All right, now after you opened up the command prompt, I want you guys to note the exact build version of your operating system. So in my case, it is Windows version 10.0.19045.5247. So I want to make sure that I note down these last few bits. Okay, so that's my exact operating system build version. So make sure to note this. After this, I want you guys to go to Google and search for this Windows x86 x64 system call table. And this website actually does a fantastic job at keeping and storing SSNs of various native API functions ranging from Windows XP to Windows 11 and Server. Okay. So next, in my case, the operating system my target VM is running on is Windows 10. Okay. So for that, what I want you guys to do is, just a minute, I'll expand it a bit. Yep. So in my case, the target operating system is Windows 10. So I'll just click on show. After this, you guys have to search up for your exact build version. In my case, unfortunately, the build version 19045 is actually not listed down here. If it's the same case for you, don't worry. We have another method to determine SSNs. Okay. But let's say that your operating system build version is 1703, which is the fourth column in this table. Okay. Now, after you determine the build version, I want you guys to search for any one of the native API functions which we are going to use in our code. So let's say that we're going to use the ntcreate thread x. And as you can see, ntcreate thread x immediately pops up. Now, the build version in our case is 1703. Okay. So 1703 actually represents the fourth column in this, which is this one. Yeah, 00B9. Okay. So the SSN for your specific Windows operating system, which has a build version of 1703, and the SSN for ntcreate thread x on that operating system is going to be 00B9. But let's say that if your operating system build version was 1607, then in that case, it would be 00B6. Okay. So as you can see, the SSNs actually vary between operating systems and operating system build versions. Okay. Now let's move on to the second method of determining these SSNs, which is via any debugger installed on your Windows system. In my case, I'm using the x64 DBG on my target Windows system. So I'll just open that up real quick. x64 DBG. And there we go. So once you've opened your debugger, I want you guys to start a random process such as notepad.exe. And what I'll do is I'll attach the notepad.exe process to this debugger. So I'll just press Alt A on my keyboard and I'll just attach the notepad.exe process. Now, let's say that you want to determine the SSN for NTOpen process on this operating system. So for that, what I'll do is I'll go to symbols over here and I'll search for the ntdll.dll file, which is usually at the end of this whole tab. So I'll just go to ntdll.dll and then on the right side, I'll go to the search box over here and I'll just type ntopen process and I'll click on the first result. And as you can see, we immediately get the syscall stub for the ntopen process. And here is the exact SSN of ntopen process on this operating system. So I hope you guys are now clear of both the methods of determining SSNs of these 4 API calls. Okay. Now, what I want you guys to do is pause this video and using any of these methods which you're more comfortable with, determine the SSNs of the remaining API calls and note them down. Once you've done that, meet me back at the video. Alright, so here are the SSNs of the 4 native API calls which we'll be using. Okay, we have the ntopen process, we have ntallocate virtual memory, write virtual memory, and create thread x. Okay. Now the next step is to write down our custom syscall stub. And for that, what I'll do is I'll go to my Visual Studio and I'll click on the syscall.asm, which we had defined previously. And Now, please make sure that you guys follow the same format which I'm following here, or else this is going to give you errors. Okay. So first of all, we start out by writing .code and end. Now, in between of these two lines, you write down the whole syscall stub. Okay, you write down the syscall stub for all the 4 functions. Okay, make sure that the syscall stubs for all the 4 functions are in between of these 2 lines, or else you're gonna get errors. Okay. Now, first of all, we'll start out by defining the syscall stub for the NTOpenProcess function. So for that, I'll just say with a tab NTOpenProcess proc NTOpenProcess NP. Okay. Now, in between of these 2 lines, I'll define my NTOpenProcess syscall stub. So first of all, the first instruction is move rt rcx. After this, we move the SSN of NTOpenProcess into the EAX register, and the SSN of NTOpenProcess in my case is 26. So I'll just say move EAX, 26H. Now make sure to add a H after 26. That is because it actually denotes the hexadecimal notation. Okay. After this, we finally do the syscall in order to transit from user mode to the kernel mode, and we end this by giving it a return instruction, okay, which is ret. And that's it. So that's the syscall stub for NTOpenProcess. Now, what I want you guys to do is define syscall stubs just like this for the remaining 3 API calls. Okay. Everything is going to be similar, just like the syscall stub of NTOpenProcess. However, the SSN will change for all the 3 functions. So pause the video, take your time, and once you're done, come back to the video. Okay, so finally, we're done with the stage 2 of implementing direct syscalls, where we have successfully defined our custom syscall stub and our function prototype. Okay, now make sure that your syscall stub looks something similar to mine over here. Okay, and once you're done, we can now move on to the final stage, which is coding the remote process injector. Now, in this video, I won't be showing you how to code a remote process injector, because that's something which I've already covered in my previous video on this channel. Okay. However, the difference here is that the remote process injector, in this case, actually utilizes these native API calls instead of the standard API calls. Okay. So we have the NTOpenProcess function, which is going to get a handle to the target process, and we have the NTAllocate virtual memory function, which is going to allocate some memory space, okay, in that target process, and we have the NTWrite virtual memory function, which is going to copy our shellcode or write our shellcode into that allocated memory space. And finally, we have the NTCreate threadx function, which is going to create a thread in order to execute that shellcode. Okay. And as far as the shellcode is concerned, I'm using a custom written shellcode, which is going to give me a reverse shell connection on my Kali Linux machine on port 443. For testing purposes, you can use MSF Venom to generate a shellcode for you and simply use it. So now finally, I'll provide the PID of the target process where I want to perform the injection. Okay. So for that, what I'll do is I'll just go to my Windows 10 dev VM or the test VM. And over here, I'll just go to file on the x64 DBG. I'll just go to file. I'll click on attach, which is Alt plus A. I'll search for notepad. And in this case, we'll be injecting our shellcode into the notepad.exe process. And as you can see that the PID of the process is 1028. So I'll just click on attach and I'll go back to my Visual Studio. And I'll just type 1028. Okay. So now we can finally build our code. So what I'll do is I'll just go to the build option over here and I'll click on build solution. And there we go. As you can see, it says done building the project directsyscalls.v6proj, and our binary, our final compiled binary, is stored over here. So before I actually transfer it to my test VM, what I'll do is I'll set up a listener on port 443 on my Kali Linux machine. So I'll just say nc-nvlp 443. And after this, what I'll do is I'll just go back to Visual Studio Code and I'll copy this directory and I'll simply transfer this compiled binary to my test VM. So I'll just go back to my Windows 10 VM. And there we go. We have the binary on our test VM. So now I'll open up command prompt in order to execute this binary. And we'll finally execute it by calling it. So it's direct syscall.exe. If I press enter, as you can see, it says shellcode at this memory region. So what I'll do is I'll just copy this memory region and I'll open up x64dbg. And after this, I'll press Ctrl G on my keyboard and I'll paste the memory address which is given by our injector. I'll click on OK. And as you can see that we have successfully injected our shellcode into this specific memory region. Okay, so this is my shellcode which is going to give me a reverse shell on port 443 on my Kali Linux machine. So if I just press Ctrl G over here, there we go. As you can see, we have the final shellcode to this memory region. Now, if I press enter and go back to my Kali Linux machine, as you can see, I have a connection from 192.168.138.35. If I press enter, there we go. As you can see, we have popped a reverse shell on this system. If I run whoami, I get actxdev, whoami/prev, and so on. Okay, so that's it for today's video. We've explored combining remote process injection with direct system calls to execute in-memory code stealthily. And this technique highlights the importance of understanding advanced concepts in red teaming and defense evasion. If you found this video valuable, don't forget to leave a like, subscribe, and stay tuned for more deep dives into offensive security. Until next time, this is ActiveXSploit. Keep learning and stay ethical.